kind of chapter 10 stuff. So regression, correlation, linear correlation coefficient. So I'm just going to move through this. So a correlation is when two things are connected, right? When one thing affects the other. So what were the examples? We've done a bunch of these. What was the crazy example I gave you? Remember with the Boy Scouts? Boy Scouts in the prisons, yeah, right? So that was a correlation. Yeah, Boy Scouts are cranking out criminals. They're correlated. They are related, but it's not causation, right? We talked about that. Linear correlation, talked about that. So you guys know how to do scatter plots on your graphing calculators, right? Okay, let's take a look at this one. This will remind you about the correlation coefficient. So here we are, we're on I'm going to jump to number 4. I think that's a good place to start. So looking at number 4, they got some scatter plots. Can you guys on your own, real quick, figure out which one is which there? So in other words, scatter plot number 1, they have 5 R values for us. Up there at the top, can you read those? It's R, here, I'll put them over here. R values. Remember, we did this problem. It'd be good to do it again, just review and remind. Minus 0.996. Minus 0.996. 1, 0.367. Negative. Am I missing one? Yeah. Oh, positive. There's also positive. Negative and positive. 0.996, 1, 0.367, and 81. Okay. So scatter plot number 1. Scatter plot number 1. Can you... 1.
That's great.
How do you know it's 1 and... Why is it 1? 1.0? Is that what we're saying 1?
Because one up, one positive, and then they're so tight, so it'd be 1.
Yeah.
1.
Are they in a perfect line?
Looks pretty close.
Yep. Looks like it. So that's the perfect 1.0, right? All right, what about number 2?
Positive 996.
Oops. Yeah, because that one's up as well. But it's
A little off.
a little bit off.
Not perfect 1.
Yeah.
They're kind of off.
0.996. That making sense? Here, let me let you keep. Is number 3?
367.
Yeah. Why? Yeah, it's just like no pattern, huh? No, certainly not linear, huh? Yeah, so it's closer to 0. Good. And number 4? Yeah, it's negative. The line's going down, but it's not an exact straight line. It's pretty close to it, though. What's number 5? Perfectly straight line going down. Good. So R is close to 0 if it's not a line. It's close to 1 or negative 1 if it's a line up or down. Okay. Good. Tonight we're going to be calculating with our calculator. Yeah, I haven't shown you. It comes off the calculator. I'm just letting you know in advance what the thing's going to mean when our calculator tells you an R value. Yeah. So maybe I should fill in some details. So basically, we're going to be calculating R tonight, which is called the linear correlation coefficient. In other words, it tells you how much the dots are in a line. That's what it basically tells you. So if the R value is close to 1, that means approximately equals 1, then the dots are pretty. They don't do that. The dots line up. The closer it is to 1, the dots line up. The closer it is to negative 1, the dots line up going down. That's kind of so-so. But, they kind of go downwards. And if the dots are just like random, meaning when you do a scatter plot, when you take a bunch of data, which we'll see in a minute, then you'll get an R value that's about 0. So that's what we're going to see. Basically, so the whole point of this chapter 10 is knowing if two things connect together. So like Boy Scouts and being criminals, right? We talked about that. And there is a relationship there, right? If you graph the states that have more Boy Scouts have more criminals. So we'll see some examples. The R is the linear correlation coefficient. Here's like a real life example. Actually it's just X and Y, isn't it? So it's just some X, Y dots. Use the given data set to complete. Here, let me. Number 7. So what they did is they took internet users and award winners for like a scientific award for various countries per 100. What is it? Listed below are numbers of internet users per 100 and the numbers of scientific award winners per 10 million people for different countries. So they took some different countries in the world, United States, China, England, whatever, I don't know what countries. They took a bunch of countries and they said, hey, do you think there's a relationship between having more people using the internet in a country and more people earning like a big international science award in that country? Like whatever the science awards are. Do you think there's a relationship there? Do you think countries that use the internet more also might win more science awards? And vice versa, countries that use the internet less might win less science awards?
It's the same example as the other one.
Which one?
Chocolate.
Yeah, it is. Did we talk about that one? Mm-hmm. Yeah, super similar, huh? I forgot we talked about that one. That's, the chocolate and the Nobel Prizes or whatever. Right. Same kind of thing, huh? It's basically better developed countries, isn't it? So better developed countries are going to have more internet users and get more science awards. Less developed countries are going to have less internet users, less science awards. Let's see if there's a relationship. So you can test if there's a relationship between those things, between internet use and science awards. So these countries, 80.6 per 100 people use the internet in whatever this first country is. And then 70, that's percent in other words, per 100%, isn't it? And then this is how many science awards. All right, so you'll have your calculators. Let's put this data in to our calculators, hit the scatter plot, and see which one. This is exactly how your homework's going to go. This is number 7. So just make that top list L1 and make the bottom list L2. So this is L1. Whoops. And the bottom list will be L2. So just put it in. To get a scatter plot, so number 1, so put the data in L1 and L2. Put the data in L1 and L2. And then hit, second stat plot. That's the button that's upper left corner, very upper left above the y equals. And then go in and turn plot 1 on, right? You got to put plot 1 on. Make sure it's on. Go into it and select. So turn it on and then select the first graph. You know, there's 6 graphs there. It could do 6 different types of graphs for you. Select the first type. And then make sure the X list is L1, which I'm sure it probably already is. And the Y list is L2. Probably already exactly that. And that'll be it. Once you've got that, you can just go second quit. Or no, you don't need to go second quit. Then just hit, zoom. And hit 9. Because the zoom button's in the top middle. And hit 9 because that's the stat graph. And it'll do a little scatter plot for you. And I'm getting, let me see, which one am I getting? Oh, is it D? Val, I hear you say D. Yeah, that's me too. I'm getting D. Getting one that looks like that? Here, I'll go back to the instructions.
Mr. Aaron, what do you do with the mark?
Just keep saying quit.
Mine too.
Probably won't happen. All right, so let's find the linear correlation coefficient. So how are we going to find that thing? Well, that thing is back on now. Now what we're going to hit is we're going to hit stat tests. Didn't we do some of this last time? I can't remember.
Linear reg t-test.
Yeah, linear regression t-test. Exactly.
On the graph you do that?
Oh, it doesn't matter whether you did the graph or not. It's like the graph's a total separate thing.
Okay.
Yeah, good question. Yeah, choose linear regression t-test. Yeah, so choose that. Don't choose t-interval. We'll do that a little bit, but t-test. Okay, so then you got to put in, it'll say what is the X list, and that make sure that's L1, And the Y list, it's asking for the X's and the Y's, you know. That's L2. Frequency is 1, like usual. And then it'll ask you whether you want a not equals, a greater than, or less than. Don't even worry about it. Just keep it on not equals. Choose not equals.
Okay.
That's pretty much what we'll always do. Yeah, just choose not equals. I'll explain in a little bit. And then calculate. So hit calculate. And so you're looking for the R value. You have to go down, I think. Yeah, there it is. I'm getting R equals 0.5924. Uh-oh, did I do something bad? So 0.76. 0.7697. Is that what you said?
Yeah, don't we round that?
Yeah, however far they say. What do they say? 3 places. So 0.7697. So let's round that to the third. Here, remember how rounding works? This one's a little more tricky. Third place, look 1 to the right. If it's 5 or more, go up. How does 769 go up?
7.70.
770? 769 goes to 770? Yeah. That good? Everybody finding that okay on your screen? The R value? Hypothesis. So how do we do this? What do you do with a null and alternative hypothesis? Well, the null hypothesis is that they already have the it's a Greek P. Well, it's a Greek R. It's pronounced rho. Yeah, do you know it? It's rho. Anyway, whatever. Just it's an R. It's basically an R. It's a Greek R. I don't know if you've noticed they always use Greek letters for the true values as opposed to the sample values. Is that making any sense? So now we survey 10 people, ask who they're going to vote for, and try to let that determine what we think all people are going to vote for, right? You with me? All statistics is comparing a sample to the real truth, right? Or we might figure out the average body temperature. Survey 100 people, get their average body temperature, and assume that's close to the real average for all people in the world. That's always what we're doing, right? We're comparing sample data to real data. So R is the sample, right? R is the sample correlation coefficient. It's just from these numbers. R is only from these, 6 countries. It's not every country in the world. It's just those 6 countries. R is just the sample number from our 6 countries. Now, what we're trying to determine is the truth about all countries in the world. Is it true of all countries that more internet users mean more science awards? Is there a linear relationship for all countries? So they use the Greek letter, which is like a Greek P where you kind of curve this a little bit. Anyway, it's called rho, almost like rho, like rho, whatever. It's just like we would use X bar and we would use mu for mean. Remember, we would use the English letters for a sample. Let me talk about units notation for just a minute. I don't ever talk about it. And Greek for the true, what they call population. Meaning what's true of the whole population, not just a little sample. Are you getting that idea? Every now and then I'm thinking I'm not emphasizing that enough. I'm not going to put a bunch of notation on the test. But the idea, you do want to make sure you're getting the main idea. And that is that we're always taking a little group, 6 countries, 100 people, whatever, taking the body temperatures of 100 people, or the internet users in 6 countries, and trying to make a conclusion about the body temperature of all people, or the country internet relationship for the whole world, the whole population. And it's always an English letter for the sample, English for the sample, the little group, Greek for the true population. So when they're over here saying, what's the null hypothesis? Rho does not equal 0. No, I'm sorry, equals 0. Let me get it straight. Equals 0 versus not equal 0. That's what it's always going to be when you're doing a linear correlation test. And the equals 0, this is R. Just think R. When you see that P thing, it's a Greek R, really. Just think they're basically saying R is 0. Am I making any sense at all?
Yeah, I keep trying to reference back like the previous stuff that we do.
Yeah.
We keep seeing those letters, but
Yeah, those letters are, like for a long time we did mu not equal to 0, or mu equals 0, mu not equal to 0, that kind of thing, right? And mu was the Greek for mean. It went with x bar. That's a Greek m, actually, for mean, for the word mean, average, mean. So that's why we were doing that. So it's to say, see how they're being consistent. That the x bar is English, so that's just like, what if we said, hey, we want to figure out the true average body temperature for everybody in the world? What's the average human being's body temperature in the whole world? Well, we can't measure everybody in the whole world. That's why we have statistics. So we just grab 100 people, take their body temperatures, that's x bar, that's the sample, right? And we try to see how strong that can lead us to a conclusion about mu, the true average body temperature for the whole population of the world. That's always what we're doing in stats. You getting the idea with that? We're always taking a small group to drive and lead to a conclusion for the whole population. So it's always, we do things with English letters, but whenever you write a null or alternative hypothesis, it's always Greek letters. You're never going to see English letters there. Why? Because you're trying to conclude something about the whole population. That's why you're doing the study. Right? I know what the average body temperature is for those 100 people. I just took their temperature. I'm not trying to conclude something about that. I know that. I'm trying to let that tell me something about the whole thing, right? Like when they poll for an election. They ask 100 people who they're going to vote for. They know who those 100 people are going to vote for, but they want to they want that to lead them to a conclusion about the whole nation's going to do on election day. Same kind of thing. Get the idea? Little group to lead us to a conclusion about the whole population. And the problem is, with little groups, you could get a weird little group, couldn't you? You could get weird people that are going to vote a weird way, or have weird body temperatures, or have weird countries with lots of internet users but no science awards. Weird things can happen, luck. Strange things can happen, right? So what statistics does is comes in and says, yeah, but how likely is that? If it's super unlikely that luck could have got in there, then we believe it's not luck. We believe there's something real causing it. You get the idea on that? Every now and then I want to beat that drum. I don't know if that's helping at all, or I'm just doing the Charlie Brown teacher, because they're looking at me and I'm thinking I'm not communicating. All right, so when you see that, so I'll go back to the problem. So when you see that little P thing, think R. It's a Greek R. It's rho, R. See, it's an R in the word rho. So it's a Greek R. So they're basically saying, hey, with the null hypothesis for linear correlation, the null is always R equals 0, and the H1, the alternative, is always R does not equal 0. Now, what does it mean if R equals 0? Remember, back here? What does it mean if R is 0? Or basically 0? No linear relationship. No, right? Look at those crazy dots. They're not lined up. They're not in a line. No linear relationship. Whereas if R is far away from 0, right? If R is way down close to -1, then there's a linear relationship going down. Or real close to +1, there's a linear relationship going up. That's what we're trying to distinguish. Is it really close to 0? If so, there's no linear correlation, right? Or is it really close to 1 or -1? In those cases, there's a linear relationship. There's strong evidence anyway. There's always the chance of luck, but there's strong evidence. All right, so here we go. So that's what the test we're doing. So we're saying the null hypothesis is that the R is 0. What does that mean if R is 0? No linear, no linear. Careful, it's linear now. There could be a curved relationship. R is specifically about a line relationship. Now there are lots of things in life that have exponential relationships or other types, curved. We are specifically and only testing for a linear relationship when we calculate R. There's other fancy statistics tests, which we won't do in this class, for higher level statistics classes, where you test for curved kind of relationships. We're not going there. We're just doing the linear test. Are these things related in a line fashion? So no linear correlation or linear correlation. If R does not equal 0, then we believe there is a linear correlation. So that's what it is, no or yes to the linear correlation. Is R close to 0 or is R far away from 0? Not equal to 0. That's the alternative hypothesis. All right, let's get our numbers. Y'all got the test statistic there? The same screen. You don't need to do any new screen. It's just the t-value that's already there. 2.411. It should be right on the screen still.
Yes.
Oh, they just want 2 decimal places, huh? 2.41?
Yeah.
Got that? And then the p-value, what is the p?
0.07.
0.073.
Yeah, there's it. 0.07. How many places do they want? 3? 0.073, thank you. 0.073. Okay. Now, so what do you think? What level did we test this at? Oh, 0.01 level. There's the significance level. See, back in the beginning, they said test the claim of linear correlation. By the way, that's always the claim. The claim is, well, I think that's always the claim. The claim is, well, I shouldn't circle that because that's not our conclusion. The claim is there was a linear correlation, that yes, there was linear correlation. They wanted me to test it, wanted us to test it. Claim of linear correlation between the two variables at the 0.01. They wanted strong evidence beyond 1% chance of luck. So did we get it? Is 0.073 less than 0.01?
No.
No. The p-value is 0.073. In other words, there's too much a chance of luck. Because you might be thinking, if I was you, I'd be saying, well, those are aligned. I saw the scatter plot. Right? It was this one. They look kind of like a line. Yeah, but they look kind of like not a line too. There's just too much chance that you could just get those dots like that by luck, and there's not really a linear relationship there. The chance of luck is 7%. So if you do something and it comes out looking good, but there was a 7% chance of luck, that's not strong evidence. There's some evidence, but that's not strong. So is it less than 0.01? No, I should reverse it. The p is not low, is it? So it's greater than 0.01. The p is not, whoops. The p is not low. So HO does not go, right? If the p is low, the null goes. But if the p is not low, the HO does not go. So we stay with the HO, which says there's no linear correlation. We don't believe there's really at least is this strong or weak evidence? Weak, right? Because the HO is always weak. So there's weak evidence. In other words, there's not strong evidence that there is really a linear relationship here. There's just too big a chance it could be luck. Those dots sort of lined up, maybe by luck.
I just used the same.
Does it make sense? We good this? See how we're concluding that? All right. So, how can we answer these questions at the bottom? Because the p-value of the coefficient is, here, let me get this out of the way. Because the p-value is, greater than the significance level, isn't it? Greater. Sorry, greater than the significance level. There is not sufficient evidence to support the claim that there's really a linear relationship between internet users and science awards. There's some evidence, but not strong evidence. There's too much of a chance of luck getting in there. So we don't really believe there's a principle involved. We good? All right, I'll move on. Questions? So police sometimes measure shoe prints at crime scenes so that they can learn something about criminals. Listed below are shoe print lengths, foot lengths, and heights of males. Construct a scatter plot. Find the value of the linear correlation coefficient R. Find the p-value. Determine whether there is sufficient evidence to support a claim of linear correlation between the two variables. Based on the result, does it appear that police can use the shoe print length to estimate the height of a male. So in other words, how do they know if that's valid? How do they decide these things? At a crime scene, can you just measure footprint or shoe print length, and that tell you something about how tall the person is? Could you be tall and have small feet? Or big feet and short? Of course, you could do lots of things. There's always weird exceptions. But is it normal? Certainly not normal, right? Usually people with big feet are taller, people with small feet are shorter. But how often? I mean, is it really that reliable? Is it beyond luck? And that's exactly what you need in a court of law, right? Evidence beyond a reasonable doubt. So, like, if there's shoe prints and you're trying to give evidence on a witness stand that means very likely this person is tall, what's very likely? How do you support that? Well, this is exactly the kind of thing we look at. Is data, and we calculate the p-value, which is the chance of luck, the probability of luck. Let's take a look. So here we go. So now, what's confusing here is we have, like, extra data. How can you tell there's 3 variables. There's shoe print, foot length, and height. What do they really want us to focus on?
Foot width and height?
Shoe print.
Yeah, where does it say that?
Says, please can use the shoe print name to estimate the height of the male.
Nice, good eye. Yeah, shoe print length and height. So really, you can just cut out those middle numbers. They're just there to confuse us. We don't need them at all. We're just trying to connect shoe print and height to see if there's indeed a linear relationship. So put the shoe print in L1, put the height in L2. Let's see what we get. And then, at least on my screen, the D, one that looks like that, this over here.
Yeah.
We do the scatter plot. Does that look like a line relationship? Sort. Maybe like kind of through there with one other dot just being off. I don't know. It's so-so. I'd say pretty much so-so. So let's go on and calculate the R and all that stuff. What'd you all get for R?
0.216.
Okay, me too. I thought maybe I was crazy. Yeah, 0.2167. I guess it rounds to 7, huh? So 217. So, okay. So sorry, I just always joke around with cell phones. Sorry. All right. So for linear regression tests, it's always equal to 0 for the null and not equal to 0 for the alternative. Always. That's just kind of nice. There's no other variation. It's always going to be that way. Well, I mean, there are some in fancy stats, but in our class, this will be all we do. So every time it'll be that way. So this will be equals 0, not equals 0. Okay, test statistic. T equals 0.38. Yeah, just 2 places, huh? 0.38, yeah. And the p-value?
0.72.
That's terrible. 0.726, yeah. So that's a big chance that this is just lucky dots that end up looking somewhat. And that p-value is way greater than this. I don't even know what the significance level is. 0.05. So that's way greater than 0.05, isn't it? Is that good? So way greater than 0.05. So what's our conclusion? Because the p-value is, yeah, greater. It's down here. Greater than. So the p is not low. So the HO does not go away. We keep the null. We believe that it's equal to 0. We believe R is 0. No linear correlation. There's no strong linear relationship here. There is not sufficient evidence to support the claim that there's a linear relationship. Okay, based on these results, does it appear that police can use shoe print length to estimate the height of a male? What do you think? Can they use that? No. What's the first one say? No, because shoe print length and height appear to be correlated. Yeah, no, that, yeah, it's D, huh? No, because shoe print length and height do not appear to be correlated. There's too much variation. I guess there's too many people with big feet that aren't tall, or vice versa. I don't know how real that data is, but there it is. That's how they make these conclusions. They need strong evidence. We good? These making sense? Okay, so number 13. Presidents and their opponents. Basically, the question is there a linear relationship between the heights? Do people running for president, if they're tall, their opponent is tall, and if they're shorter, their opponent is shorter? Is there some kind of relationship? The media sometimes talks about that. It seems kind of dumb to me. But is there a linear relationship between a presidential candidate's height and his or her main opponent's height? There's the numbers. Put them in. I'll do it real quick. Looks like you guys are off and doing your homework. That's great. L1 for the numbers on the top. L2 for the numbers on the bottom. Like getting your homework done, getting stuff done. So I'm doing the president one. And so, you don't have, when you do the Scatterplot, just hit zoom 9. You don't need to redo all the stuff every time. You don't need to do second stat plot every time. That's what I mean to say. Just hit zoom 9. Once you've got the second stat plot set up, just hit zoom 9. It'll graph the new one. They all kind of look alike. Yeah. Wait, is it? Yeah, I think you're right. Yeah, good eye, Val. Yeah, it's that one, isn't it? That is not linear, is it? I don't think. All right, I'm going to go do the test, linear regression. Regression t-test. Boom. All right, so I'm getting R equals 0.137. Yeah, that's terrible. The null is always equal to 0. The alternative not equal to 0. Here, so equals 0, not equals 0. The test statistic t equals 0.48. They went two places. 0.48. The p-value 0.6395. Yeah, we got to round that to 0.640, huh? Right, round to three places, so 640. All right, that's totally a big p-value, way bigger than whatever their level was. 0.05, 0.01, no way. So the media is crazy. If the media is saying there's something going on to heights, this gives strong evidence the media is wrong. There's no strong evidence. So the p-value, the p is again not low. So the HO does not go. All of our results have kept the null hypothesis. R is 0, no linear correlation. Almost everyone I've done, I think everyone I've done tonight has been that way, hasn't it? Because the p-value of linear correlation is greater than the significance level, there is not sufficient evidence to support the claim. Should we expect that there would be a correlation? No. No, because presidential candidates are nominated for reasons other than height. I sure hope so. Not good? Thinking questions. 20 different stat students are randomly selected. So like you all, what are you, 25 of you in here? Each of them, their body temperature is measured, so they measure your temperature, and their head circumference. Now, why are they picking those two? Do you think how big your head is? Think bigger heads have higher temperatures and smaller heads have less, or vice versa?
Your head holds your heat.
And nothing. There's no relationship there, huh? They're just picking something totally dumb, right? Do you see what they're doing? There's no relationship between how big your head is and what your temperature is. That's silly. So they're picking two things that are not related. So they want you to know they're clearly not related, and then and tell them what that means about R and all that stuff. So, okay, so they do that. For this sample of paired data, what does R represent and what does rho? Oh yeah, so they're questioning you here about the English and the Greek. Remember what I said about that. R is the English. Obviously, that's a letter in the English alphabet. And this funny looking curvy P thing is actually rho. It's Greek. It's a Greek R, basically. So they use the English and the Greek of the same letter. That's what they always do, basically. Now, why? What's that mean? What's the Greek? What's the English? What do they mean? Did you catch anything I said earlier? Yeah, one's a sample. Which one's a sample? Yeah, the English is always the sample, like the whatever, the 20 stat students, right? Oops, I hit the wrong button. The 20 different stat students, their whatever, their linear relationship, and the Greek is like, is there a relationship for all people in the world between their head size and their body temperature? All right, so choose the correct answer. R is a statistic. R is a statistic. Is that right? Yeah. R is a parameter. No. D's already out. Remember, parameters go with population. It's been a long time since we used that word. It's been like 2 months. I don't suppose you remember. Populations go with parameters. Samples go with statistics. S and S, P and P. Yeah. So, good memory, Val. Yeah, so that one's out. So this population is a parameter. So that's out. So I don't know how to eliminate anything else. R is that represents the value of the linear correlation coefficient. Is that the wind out there? Oh, okay. All right. Yeah. That represents the value of the linear correlation coefficient computed from the paired sample data, and P is the parameter that represents a portion of the variation in head circumference that that can be explained by variation in body temperature. Okay, wait, that sounded good. Yeah. Wait, they all sound good to me here. These are tricky. I think it's B. What's wrong with A? What's wrong with C? And P is a parameter that represents the value of linear correlation that would be computed by using all the paired data in the population of all. They all sound good. I'm sorry, guys. All right, so much for B. The answer is C. What's wrong with B then? Oh, R is the statistic that represents the proportion. It's not the proportion. So that's kind of dumb. And P is the parameter that represents the proportion. No, okay. I didn't notice those. They snuck in those words. All right. I'm not going to test you like that. That would be unfair. So, yeah, they just snuck in bad words right in the middle of a bunch of good words is what they did. Sorry, I looked at it ahead of time quickly and thought it looked like generally a good question. It's not a very good question. All right, let's go on down to B there.
Oh, no.
Just cut out the two that have the word proportion in them. They're no good. And the one that has parameter. Yeah, so the two that have proportion and the one that has parameter are not the right answers. Those aren't proportions nor parameters. All right, let's try this one. This one will make more sense. Okay, select the choice. What do you think R should be about? Is there a relationship between head size and body temperature? No. So what is R then? R is about 0, isn't it? I'll put shaky equals. It's approximately 0. It's close to 0. Okay, so the value of R is estimated to be 0 because it is likely that body temperature and head circumference are strongly correlated. No. So it's not that one. It's got to be B because that no correlation exists. Yeah, there it is. 0. C. Choose the correct answer. The value of R does not change. What was C? Did they do? And it says, does R change if body temperatures are converted to Fahrenheit? If you change from Celsius to Fahrenheit or whatever, no, I won't change anything. It doesn't matter what your units are. So, the value of R does not change because R is not affected by X or Y. That's not true. Does not change because R is not affected by converting all values to different scale. Yeah, different scale. That's it, yeah. All right, enough with that crazy question. All right, let's try number 2. 20 different stat students are randomly selected for each of their body temperature, same thing. It's found that R is 0, as we'd expect. So if R is 0, does that indicate that there is no association? Careful. Remember, if R is close to 0, that doesn't mean there's no relationship. What does that mean? There's no linear relationship or correlation, same thing. But so in other words, there could be a curved relationship. It just means there's no linear. R is just a test of linear connection, straight line connection. That's what they're making sure you're clear on. So does it indicate there's no association? No, because there's no linear. There may be some relationship that's not linear. That's it. Okay, C3. Here we're going to do global warming. Number 3. If we find that there is a linear correlation between concentration of carbon dioxide in our atmosphere and the global temperature, does that indicate that changes in the concentration of carbon dioxide cause? That's the key word they're throwing in there. So if we find that there's a relationship between those, does that mean that one thing is causing the other? No, not necessarily. I mean, of course it might be, but that alone is not evidence. You'd have to do other things, right? So they're just making sure you know that correlation is not causation necessarily. Boy Scouts were not causing more criminals, were they? There was a connection. States that had more Boy Scouts had more criminals, but that wasn't a causation relationship. Boy Scouts were not causing more criminals. Those states just had bigger populations. They had more of everything, right? Remember all that? So they're just testing that to make sure you know. Correlation does not imply causation necessarily. There may be causation, but you can't just say for sure. Okay, so 17. When determining whether there is a correlation between two variables, one should use a blank to explore the data visually. So which of these, what should you do to display?
Scatterplot.
Yeah, scatterplot. They're just saying you should do a scatterplot. Okay, 18. Which of the following statements about correlation is true? We say that there is a positive correlation between X and Y if X values increase as the corresponding Y values decrease. Is that what a positive relationship means? Think about a positive graph. Dots that go like that. They both increase, right? Because this is X and Y. X numbers get bigger in this direction, don't they? Y numbers get bigger in this direction. If it's positive, they're both getting bigger together, aren't they? So not A. X increases, Y increases. There we go, B. They're just making sure you know what it means for two things to have a positive relationship. One goes up when the other goes up. If hours studying and GPA, right, if I was to do a graph, how many hours per week you do homework and what your GPA is, probably there would be a positive relationship. More hours, more GPA. Positive relationship. Right? Remember we talked about those kind of relationships last time? Almost like a trick question. It's the linear correlation coefficient. Measures the strength of the linear relationship. All right.